This is my verbal explanation of your AP classroom assignment related to Unit 7, Conservation of Angular Momentum. Okay, so this is number 1. You got a rod here that has a pivot point around this axis of rotation, and the rod is at rest, and it's on a flat horizontal surface, but we have no friction with that, I'm assuming. And they have a um, sphere, piece of clay or something that's going to um, travel in a linear direction and hit at the end of the rod. And does it stick, is what I'm trying to say. Yes, it sticks to the rod. And the both objects, if you can imagine, the rod and the sphere will then start to rotate, okay? And they want to know what we know about the angular momentum and the kinetic energy, rotational kinetic energy, of the sphere rod system before and after the collision. Well, if the system is defined as the rod sphere system, and it's on a frictionless surface, which they may have not done a good job of explaining that, but it should have, then we have no outside torque on the system, and it's a collision. So we know that the angular momentum is conserved. And so let's look at what that means. So initial angular momentum has to equal final angular momentum. Um, I am going to go look at the answers and notice that right away, angular momentum immediately before the collision is greater. Angular momentum before the collision is greater as compared to after. And I will immediately eliminate A and B from my options because we know that angular momentum is conserved in this type of situation. And so I know that the angular momentum is conserved, so it's equal. And so let's go look at just all the equations that are related to that. I have the initial equals final. What's the initial angular momentum of the system? It's the initial angular momentum of object 1, which I called the sphere, plus the initial angular momentum of object 2, which I called the rod. The rod has no angular velocity, so it's 0. So the initial angular momentum is the I value of the sphere times its angular velocity of the sphere. Well, the I value of the sphere, we're going to consider it a point particle. So it's m naught, the mass, times its distance away from the axis of rotation squared, times its angular velocity, which I'm going to use the bridge equation to determine it based on the item I know, which is this linear velocity. And that here's the bridge equations, and here's the angular velocity solved for based on linear velocity and the distance away. So again, the final momentum of the system is equal to the mass, right? This is just the mass, rotational inertia of the system times its final angular velocity. Well, I can add those two I values up and then multiply it times its angular velocity. Now set those two equal to 0. Initial angular momentum, which I didn't sub in all the things, but I'm just using this as a way to show you, is equal to the final angular momentum. And notice that the rotational mass had to go up. So we know this angular speed had to go down, okay? But those total angular momentum on each side before and after is the same. All right. So again, I was only using that as a way to explain all the math related to that. Okay, angular momentum in C and D, they tell me that angular momentum is equal to. Great. I got to now determine which one's correct, C or D. Well, now they talk about kinetic energy immediately after, and C is the kinetic energy before the collision is greater than after. Or D, the kinetic energy before the collision is equal to. Well, equal would mean that it was was an elastic collision. And if you recall, you have to be told that. And they didn't tell me it was elastic in here. So since L is conserved, whoops, go back. Since angular momentum is conserved, the angular velocity went down because I went up. You can see that it went up. And so kinetic energy, which is the product of the I value times the velocity squared, goes down because the velocity, angular velocity went down and it's squared, so it has a larger impact on the kinetic energy. So, okay. All right. Conservation of angular momentum. Oh, sorry, number 2. Situation is I got a ball. It's traveling with a velocity v naught. It has somebody holding a string, and it's providing a force of tension directly towards the axis of rotation. And as the ball travels in the circle, we're going to pull inward with and make the radius smaller. So you can see that this radius here is getting smaller, and we want to know how that impacts angular momentum and rotational inertia of the ball. All right, so just look at this. The force of tension points directly at the axis of rotation. That provides no torque on the ball. There is no torque acting on the ball because it is directly towards the axis of rotation. So the net torque there is 0. Therefore, momentum is conserved. Convince yourself I have no torque acting on the ball that is directed directly towards the axis of rotation. So I'm going to go through and eliminate options A and B because it tells me angular momentum increases when C and D says the ball angular momentum is constant. Then I got to evaluate whether or not the rotational inertia, which is I, goes up or down of the ball. Well, I equals mr squared. The mass of the ball isn't changing. R is decreasing. And therefore, since R is decreasing, I is decreasing. And you'll see that C tells me that the rotational inertia decreases. Number 3, I got a planet rotating around the star. The only force that's acting on the planet that's going around this perfectly circular orbit is force of gravity, directed straight towards the axis of rotation. Therefore, it goes right through it, and that force of gravity does not create a torque, and there is no outside torque on that. There's an outside force on the planet, but there's no outside torque about that axis of rotation. And they want to know what graph predicts the angular momentum of this planet as it travels from point A to point B. Well, if there's no outside torque, then I cannot change angular momentum. Again, torque times time equals change in angular momentum. The net torque is 0, so the change in angular momentum is going to be equal 0. And the only graph that shows a constant angular momentum is C. Number 4, I have a situation where I have a disk. It's rotating at a constant angular speed omega subscript d. This disk has a piece of clay that's going to come down out of the sky and hit and stick on the disk. This is analogous to a cart, traveling at some speed, and then a mass falls into it. And now I have 2 masses inside the cart. Mass goes up, velocity has to go down. If we assume no frictional forces are involved, then momentum is constant. Okay, and same thing here. We will assume that the angular momentum of the system, the disk ball system, is constant. And again, all right. In this experiment, the disk has no friction. The disk is set into motion and rotates with a constant angular speed. As the disk spins, a small piece of clay drops onto the disk and sticks. Which of the following claims is correct about angular momentum and total kinetic energy? Okay, well, I've just got finished saying there's no outside torque. Angular momentum has to be conserved, so immediately A and B are not an option. Now I have to determine, does kinetic energy go up? Or sorry, does the kinetic energy go down? Because C would mean that it would go down because it was greater before the collision. Or does kinetic energy stay the same? Well, since the I value, I goes up and omega goes down, but omega is squared, and that is why kinetic energy goes down. Besides, the only way that this type of collision would have a conserved kinetic energy is if they told you it was an elastic collision, which it is not. And that's very similar to what we had before in this situation. In linear land, mass goes up, velocity goes down, kinetic energy is equal to 1/2 the total mass, ma, plus mb, times velocity final squared. And so even though the mass went up, the velocity goes down and it's squared. So we lose energy. Okay, number 5. We have, again, a disk or a piece of clay or a sphere. I'll call it object 1. It's traveling with a linear velocity towards a rod of length L, and the rod is currently not moving. Okay, so that's before the collision, and then it's going to either bounce or stick or something. I can't remember. Okay, it's actually, the disc is going to come to a complete stop, and then the rod is going to take off at some angular velocity omega-2. And they're going to ask some things. They're going to ask, which of the following procedures can you determine the final angular velocity of the rod 2? We're trying to find omega-2. So I'm just showing you all the things. So the initial angular momentum of the system has to equal the final angular momentum of the system because there's no outside torque on the system itself. The system is defined as the sphere and the rod. Okay, so I'm going to break down what the equation is for the final angular momentum of the system. Well, it equals to the final angular momentum of the disk plus the final angular momentum of the rod. Well, what's the final angular momentum of the disk? Yes, it does have velocity, but velocity drops out of the sky and now drops straight down in an x direction. It's no longer traveling in the y direction. And now that means that that tangential velocity is 0. So that velocity, since there's no tangential velocity for the disk anymore, its final angular momentum about that pivot point is 0. So the only momentum of the system after the collision is I2 times the angular velocity of the rod. Okay. Angular initial of 1 has to equal the final system momentum, which is I2 omega-2, and I just basically created this equation. Initial equals final. Well, what do we know? They told us I1, which they said in the thing is I sub s. They told us I2, which they called IR. They said we have it. They also told us the length of the disk is L. And if I know the velocity, V naught, which they told us originally up here, okay, I know omega initial. So I know everything. I can find omega-2. So let's look at B, A and B. First off, A and B are the only two that I'm even going to look at because they say the momentum is conserved. In C, they tell me energy is conserved. No, nowhere did they say this was an elastic collision, so energy is not conserved. So in addition, D is not correct. Notice A, the initial angular momentum of the sphere as measured from the end of the rod. This is not correct. Okay, no. Look at B, the initial angular momentum of the sphere as measured from the pivot. So that's how you would do it, because that is the axis of rotation. Okay, don't freak out over all the things. I'm trying to just help you see all my math. Again, same scenario. I have a piece of clay. It's hitting a sphere in 3 scenarios, and it's sticking. In all situations, the initial velocity of the clay is 8 meters per second, okay? All of these are collisions that stick. There is a conservation of angular momentum. The initial angular momentum is going to equal the final. So if I know the initial angular momentum, then I will know the final angular momentum. Well, what is the definition of the initial angular momentum? Well, the only thing moving before the collision is the little piece of clay. So if I know the I value of the clay about these axis of rotations, Okay, if I know the I value about that axis of rotation, and I know its angular velocity about that axis of rotation, then I know the initial angular momentum. So I have the mass of the clay. I know the L's of the clay in every situation. Don't forget to square it. The angular velocity of the clay initially is the linear velocity divided by the length again to the axis of rotation. So I calculated it for each scenario, and then I ranked them, and that would be D. Last one, I think. I have a situation where the ball or the mass of the clay hits the stick and sticks. The only, again, no outside torque. Initial angular momentum of the system has to equal the final angular momentum of the system. The only thing that's traveling or has an initial momentum of the system is object 1. Has to equal the final angular momentum of the system. I don't know why that changed to green. They want to know the ratio of L1 to L2. That's the final. So I want to know L final of 1 ratio to L final of 2. That's just a fraction. L1 final over L2. Okay. So if I can calculate the initial, then I know the finals, and I have the ability to calculate the initial. And so let's go look at how to do that. Initial of the system is the I value of the disk times its initial angular velocity, the I value of the disk times its, now I converted that to using my bridge equation. Then I looked at the I calculation, the mass times, now look at the first one. Where is it located? About the pivot point. It's time 2r, and I square it. Again, the initial velocity divided by the distance away, which is 2r again. So over here in number 2, be careful. Look at where it hits. The I value is the mass. Let's go back. The mass times its distance from the axis of rotation squared. Its distance is 1.5, 3. It's instead of 3, it's half of 3. It's right smack dab in the middle. So 1.5 r. I square it, and then I determine its angular velocity in using the linear velocity. Again, the r is 1.5 r. So this is 1.5 m times r times v naught. This becomes 2 m r times v naught. Now divide them. That's all the ratio is, 1 over 2, and that gives me 4/3. It gets 2 over 1.5, and then that becomes 4/3. Okay, multiply 2 by 2 is 4, and multiply 1.5 by 2, and that's how I got 4/3. Okay. All right, that's it for conservation of problems from AP Classroom.